Lecture 1, Inventory Control with Known Demand, Part 3. So here we are going to have the first inventory model, which is EOQ model, Economic Order Quantity Model. So this is the basic model and the most simplest model that we have in inventory control. So here, these are our assumptions for this simple model. So here we assume that demand is known and fixed at lambda units per unit time. For example, let's say our unit time is year, and let's say we assume that our demand is known and fixed at 1,000 units per year. So we know that for a year ahead, we will have exactly 1,000 units as demand for our good. Okay. So in this simplest model, we assume that shortages are not allowed. Later, we will relax this assumption to have the model with having shortages. But here, we assume that there is no shortage. And here we assume that orders are received instantaneously. I mean, there is no lead time. The time that we place an order, we will receive the order immediately. So there is no delay here. So this is actually a simplifying assumption here in order to have a simple model, but later we will relax this assumption. Okay. And the cost structure here are these. So we consider the fixed ordering cost as K. So it will be dollar per order. Okay, fixed cost dollar per each order. And the marginal order cost C will be dollar per unit order. And the holding cost H here, it will be a dollar per unit held per unit time. Okay. And with no loss of generality here, we assume that the inventory level on hand at time 0 is 0. Okay. And let Q be the size or the quantity of the order. Okay. So here actually we do have a trade-off between the inventory holding cost and the inventory ordering cost. So if we have large quantities for our orders, then we will have high holding costs and low ordering costs. So why? Let's say here up to here, from time 0 up to here is a year. So if we consider larger amounts for the order quantity, then we will have less ordering over a year. So here, for example, we have one, as you see here, let me show with, so 1, 2, and 3 orders. Okay, we do have 1, 2, 3 orders, and so we have 3 orders, but the average inventory level is at this level, right? And but in the case of having more orders in a year, so here, as you see here, in a year, we do have 1, 2, 3, 4, 5, and 6 orders, 2 times. Comparing to the previous case, we do have 6 orders over a year, and as you see here, the number of orders is higher than the previous one, but the average inventory holding is lower than the previous case. Okay, so when we do have small quantities for order quantities, order size, and many ordering per year, then we have low inventory costs and high ordering costs. But if we have larger quantities, then we have high holding costs and low ordering costs. So what's the optimal level? I mean, what's the optimal level for order quantity and the optimal number of ordering per year? So we are going to actually obtain this optimal levels in order to minimize the total cost of inventory. Okay. So this is how we formulate our problem here. Q will be sorry, Q will be the order size, and here the capital T will be the order period. I mean the time that we will place a new order. Okay, so every T periods we will place a new order, and here the slope of this curve for inventory level is minus lambda. So lambda here is our fixed and constant rate of demand per year. Okay, so we are going to optimize the Q. I mean to obtain the optimal level for Q order quantity in order to minimize the total cost of inventory per unit time. Usually it's a year. Okay, so to do so, at first we need to obtain the objective function. I mean the function for the average cost per time unit per year. So here this is our objective function, or the function of average total cost per year. So let's see what are these terms here. Lambda over Q. So what's the lambda over Q? So the lambda is our demand per year. Let's say it's 1,000, right? And 1,000 units. So let me write here. So let's assume that lambda is 1,000. Okay. If we assume that Q is 100, this means that anytime that we place an order, it will be with the quantity of 100. So since our demand per year is 1,000 and we need to satisfy the 1,000 units per year and our ordering size in 100, this means that we will have 10 orders per year, right? So lambda over Q, or here 1,000 divided by 100 will be 10, the number of orders, okay, orders per year, right? So the lambda over Q is the number of orders, and in the parentheses we do have K plus CQ. K is the fixed ordering cost. Anytime that we have an order, we have a fixed cost, which is K, and C times Q is the purchase price, the purchase cost, sorry, the purchase cost. The purchase price is C per unit. If you multiply this by order quantity, which is Q here, so the CQ will be purchase cost plus K, the fixed cost for ordering. The total cost for each order, each purchase will be K plus CQ. And since we do have lambda over Q orders per year, by multiplying lambda over Q by this term, we'll have the total ordering cost per year. Okay, and the second term here is the average inventory holding cost. As we saw previously, when we have Q here, and so the inventory level will be like this. Okay. Okay, so yeah, we order Q. We do have since we don't have lead time, we'll receive the order right away. So we will have Q units in our inventory. So we will continue selling the good with the rate of lambda. The inventory level will be decreased. Whenever it reaches to 0, we will place a new order, and again we'll receive the Q units right away in our inventory, and so on. So this is our inventory level. So the average here will be Q over 2, right? So Q over 2 times H will be the average inventory holding cost. And since the time period here is unit time per year, so this means that we need to multiply this by time unit, since it's unit time, so it's 1. So yeah, so here, as you see here, we do have the ordering cost and the holding cost. Okay, so we do have this terms for the annual average annual cost. Now that's our objective function, right? So here we want to minimize this cost function. So in order to minimize this in terms of Q, I mean, our variable here is Q, ordering size. So we need to take the first derivative of this cost function with respect to Q. Then by doing that, we will, and then setting that to be 0, we can obtain the value for Q, okay, which will be this. Q star will be square root of 2 times K times lambda over H. Okay, so yeah, the square root of 2 times fixed cost times the annual demand rate divided by the unit holding cost. So that will be the economic order quantity, or EOQ. Okay, so that's our formula to obtain the economic order quantity, or EOQ. So here Q is increasing with both K and W and decreasing with lambda, yeah, with H, sorry. So yeah, as you see here, since K and lambda are in the numerator, so Q is increasing with K and lambda, and it has an indirect relationship with H, so Q will be decreasing in H, unit inventory unit holding cost. Okay, and that's it. So this is our first and most simplest and the basic inventory control model, which is EOQ. Okay. So here I'm going to show you that how we do trade-off between the inventory holding cost and the inventory ordering cost in order to obtain the optimal level for Q. Okay, so I see here H times Q over 2, which is the average inventory holding cost, is increasing in Q in linear form. Okay, and this graph will be the average inventory ordering cost, and as you see here, it's decreasing per Q. If we increase the quantity size, we will have less orders per year, right? And so this is our inventory ordering cost, and the total cost here is this this curve. Okay, this is the total cost here, the sum of these two components, inventory holding cost and inventory ordering cost. So as you see here, this total cost is in convex form. Since it's convex, so it has one critical point here, which is the minimum of this total cost function. And by doing that analysis, that we take the first derivative of this total cost function with respect to Q, and then setting that to be 0 and solving that for Q. So that Q will obtain here as Q star, which will be in the on the minimum point of the total cost function. Okay, so here we do have the optimal total cost formula, which is this square root of 2 times lambda times K times H plus lambda times C. So yeah, if we consider the order quantity as the EOQ or Q star, then the average total cost per year will be obtained by this equation, square root of 2 times lambda K H and then plus lambda C. Okay, let's have an example here. Here we do have a bookstore at a university and want to decide when and how much to order pencils to meet the annual demand. Okay, so the purchase price of a pencil is 2 cents and the sale price here is 15 cents. And the other information are as follows. So the lambda here, the demand, we estimate that, we forecast that the demand per week is 60 pencils. So since we want to have all the parameters in the same time unit, so let's convert this to annual demand. So since it's per week, so if we multiply 60 by 52, then we will have 3,120 pencils per year as our demand. Okay, and K, the fixed ordering cost here is assumed to be $12 per order. So the K is $12 per order, and here we assume that the aggregated interest rate is 25% for inventory holding cost, and we need to multiply this interest rate by the purchase price, which is 2 cents here. So by doing that, we'll obtain the H as this number as the inventory holding cost per unit per year. Okay, so now we do have all parameters that we need to calculate the Q, and as you see here, all are in the same time unit, all are per year. Okay, so this is the equation for EOQ. So 2 times K, which is 12, times lambda, which is 60 times 52, or 3,120, divided by the H, which is 0.005. So the Q star here becomes 3,870 units as our order quantity or order size. Okay, so by having this EOQ here, the cycle time will be Q over lambda, right? So as you see here, the Q here is greater than the lambda. So this means that the order, the cycle time for order will be 1.24 years. So this means that anytime that we place an order, that will be a quantity that will meet a time period more than a year. So anytime that we have a new order, we'll place the requirement for satisfying demand for 1.24 years. Okay, and the average annual holding cost here will be Q divided by 2 times H, right? So Q here is 3,870 divided by 2 times H, which will be 0.005. So that will be the average annual holding cost. And the average annual ordering cost is lambda over Q times K, right? The number of orders that we have per year times the fixed cost per order. So again, lambda here is 12 times divided by 3,870 times 31.3120 as the lambda. This will be the average annual ordering cost. So I see here in the EOQ model for Q as the Q star, always half of Q times H is equal to lambda over Q times K. Okay, so yeah, in the optimal quantity for Q, the average annual holding cost is exactly equal to the average annual ordering cost. Okay, let's have a discussion here for the EOQ policy for the bookstore example. So as you saw, the EOQ here is 3,870 units, which will be for 15 months. So this means that anytime that we have an order, it will be for 15 months, not for a year. Okay, so what issues could arise when trying to implement this solution? Okay, so the first issue here could be space. right? So we want to see if this optimal solution is feasible for the bookstore. So does the bookstore have enough space to store the requirement for 15 months? If yes, that's fine. And the second issue here will be the cost. Does the bookstore have enough budget to purchase the requirement of 15 months and then keep that in the inventory? If yes, so there's no problem to implement that optimal policy. But if we do have problem, we can say that that optimal solution is not feasible for this bucket. So in that case, we need to go with a different approach to obtain the order quantity. Okay, and the another thing here that here we consider the sale price for the pencil as 15 cents. Okay, 15 cents. So if we increase the price to 20 cents, then would that impact on our optimal order quantity? The answer here is no. As long as the lambda and the c remains constant with no change, then there will be no change in our optimal order quantity. But if increasing the price of pencil has impact on the demand rate, if it reduces the demand rate and the lambda changes, then yes, it will impact to our optimal order quantity. Okay, so yeah, that's the last slide of part 3. So by having these 3 parts of lecture 1, actually we have covered the material for the first week, and so in the next parts we'll see how we can extend this simple EOQ model by having more and more realistic actually assumptions in the inventory model. Okay, thank you.